Maarten Rijs University. So my background is applied mathematics, microlocal analysis, scattering theory, and I've been for a couple of decades involved in studying the Earth. So we have earthquakes or ambient noise that we correlate, so we do measurements at the surface of the Earth in arrays of sensors. And from that we would like to tell what the material properties, say elastic material properties inside the Earth are. So suppose I do particular measurements and the Earth would satisfy certain conditions. Can we actually uniquely recover what is there? So can we get an incontrovertible result? Then sort of the next question is, uniqueness doesn't help you to do it. So you study questions like stability. And if you have proper stability, and you can prove that typically conditionally, because intrinsically these problems are ill-posed, then you can come up with procedures for reconstruction or estimation. And that then leads to a whole array of techniques and developments, say in numerical linear algebra, to find reconstructions of the Earth, make images of the Earth. Many things. Say if we start from the deep interior, the properties of the inner core, it's anisotropic structure, it's dynamic structure. Then we are very interested in what is happening in the outer core. For example, what happens in the vicinity of the core mental boundary. And then we try to really reconstruct models for the entire mental, which is interesting from a whole variety of points of view, geodynamics, mineral physics, but starting just from the chemical composition. Now, all these problems are very interconnected. But ultimately you would have a global dynamical description of the Earth which couples all the way, say, to plate tectonics and to hazards. I came from a physics background, and via total coincidence already a couple of decades ago with my current collaborator at MIT and Rob Vanderhilst, we stumbled upon each other and asked ourselves a question about a solid state phase transition in the deep Earth, the core mental boundary. And we thought, well, let's try to find it by techniques of mathematics, and he came from seismology. And when we started doing that and were successful, the problems just mounted up and became so interesting that I stayed connected to the earth science and seismology and geodynamics community. We still don't have a way of understanding what happens in the inner core, all the way how that influences what happens, say, right at our plates or at the crustal level. And so the complexity of the physics helps you actually to get much stronger results than you would get in a simpler mathematical framework. Same is true, for example, in the nonlinear wave interactions, nonlinear elastodynamics. Complicated to understand, to describe, but once you do, then that leads to opportunities in inverse problems to tell something about the interior. I probably would be a musician. I studied music in my young years, but turned into a scientist, but I still have a passion for music and I still play music. Viola. I still play, yeah. We still play in groups actually with other mathematicians and physicists around the country, and on occasions we play. So yeah, we still do.